Yeah. Hi, my name is Kristine, and thank you for joining my PhD defense. It's nice to see so many people. And well, as said, I've spent the last 3 years working on fatigue damage evolution in fiber composites for wind turbine blades, which is what I will talk about today. And I've done so in collaboration with a lot of different people. For example, from Manchester X-ray Imaging Facility, LM Wind Power, and as part of the Cinema project. And I've also done some internal collaboration with, for example, DTU Compute, and also been collaborating with Waseda University in Japan. So I'll just mention that. And just before starting, I'll just say that there are people watching online. Please turn off your webcam and microphone now. But I'll just start by lining out the long-term vision, you can say, of my project. So where does it fit in? The idea is to use this X-ray computed tomography technique to obtain look at the 3D microstructure of the material that's considering. Using this in maybe 2 ways. One way is to observe the fatigue damage, and another way is to quantify the microstructure, so look at the microstructures, and see, can we link these two together somehow? And more specifically in relation to observing the fatigue damage, we do this in first at one point in time, so one damage state, and later also all over time, so watching the damage actually progress. And you can see what you can use this for is, for example, for some modeling purposes, where the idea is then to use this initial knowledge at one point in time as, you can say, input to making a realistic model, and using this microstructural information as input to the model, and then also using this over time studies to validate a model and so on. So this is the, you can say, the perspectives. And my PhD project is mainly focused on this point of observing the fatigue damage using X-ray computed tomography. But I've also done collaborations with Monica, you cannot see it, so I'm sorry about this, Monica Jane Emerson from DTU Compute on this quantification of the microstructure. So I'll start out by give some brief introduction to the subject. So first, why is fatigue a concern for wind turbine blades? And well, wind turbine blades experience a very high number of fatigue load cycles, so repeated loading during their lifetime of 20 to 30 years. And because of this, fatigue is a major design concern when designing these blades. However, the fiber composites used to carry the main loads in the blades are actually, the damage mechanisms in fatigue are not very well understood. And that's, you can say, the main motivation for looking into this problem. So if we look a little bit more specifically, here's an example of a cross-section of a wind turbine blade. And you actually made most of it is air, so this is a hollow structure. And then the green parts marked here are the parts carrying the main fatigue loads. So if we look at the load from the gravity, from the weight of the blades, then what we get is that this results in some what we call edgewise bending of the blade, repeated bending, which gives a tension, compression, fatigue behavior, so it's making pull and compress. And that is mainly carried by the parts out here in the blade. And if we look at the aerodynamic load, so from the wind, that causes this flatwise bending, which depending on which side of the blade is either compression, compression, or tension, tension type of fatigue. So you can say it goes from compressing less or more to cooling less or more, so to speak. And I'm considering this tension, tension part of the fatigue loading. But I mentioned these fiber composites now a few times, but what is a composite material actually? And simply stated, you can say it's combining 2 different materials or more into a new material with some set of interesting properties that can be useful. And a group of composites is then these long fiber reinforced polymers, as I'm considering in my project, which is combining a polymer matrix, so for example epoxy or polyester or vinyl ester or similar, with some long fibers that can be glass or can be carbon or other things, to form a fiber composite which is generally strong and stiff and also tough, and relatively lightweight usually. And aside from wind turbine blades, they're also used for bikes and sports equipment and airplanes in the space industry, and even also in cars, usually, and a lot more, I'm sure. So they're quite widely used. More specifically for wind turbine blades, what is actually used, or often used, is these non-crimped fabric-based fiber composites. And the principle here is that you have the fibers in bundles, lined bundles, that are put on top of each other, so in layers you can say, layered on top of each other, and then stitched together using a stitching thread, which forms a fabric, for example, like this one. And then what you do is that you stack these on top of each other, which I tried to show systematically here, while dry, and then you can, it's often infused by this resin using vacuum infusion molding or transfer molding to form the final composite. And even more specifically for wind turbine blades, what is commonly used is these unidirectional or quasi-unidirectional, as they're only almost unidirectional composites, since the loading conditions are very specific in the blades. So I've shown two examples of these type of composites. There's one where we have the unidirectional fiber bundles that carry the load. They're thicker than these thin layer of off-axis fiber bundles that are present. And these fiber bundles are actually just present to keep the unidirectional fiber bundles aligned because they have to be stitched to something during manufacturing to form this fabric structure. And this is two examples, one with plus minus 80 degree, which is the one I have here, and also another one, which is an example of 45, plus minus 45 and 90, which is this one I have here. So, yeah, this is the vacuum fiber bundles I mentioned. And now, if looking at the actual bundle structure inside the composite, so after infusing the bundles with resin, then we don't actually see this perfectly shaped bundle structure. And we, you can see this maybe here. It's just an example of an X-ray CT image of the bundle structure, where you have the unidirectional bundles here, and you can see they're not perfectly ovally shaped. And also the vacuum fibers, maybe they're not completely plus minus 80 degree orientation, as is this example here. And if you zoom in, it's also more clear that the vacuum, the unidirectional fiber bundles here are not perfectly shaped. And also you can see the fiber level as well, that they are not, the local fiber volume fraction is varying depending on where. So, and it will be more clear later that this is actually quite important to include when looking at the fatigue damage. So, back to fatigue. So, how do we actually test these materials in fatigue when designing the blade? What is usually done is to manufacture a composite plate, so a plate of this material, and you cut it into some coupon test specimens, which is, for example, like this one. It's a common one for these unidirectional composites. And then you perform these fatigue tests. In this case, a tensile fatigue test, where the maximum, the ratio between the minimum and the maximum load is 0.1. That's the case I consider, but you can also test for other cases. And with a sinusoidal wave shape, and what you get from such a test, if you, for example, measure the strain by extensometers or similar, then you can calculate the stiffness degradation of these materials as a function of the load cycles applied. So here is an example of some stiffness degradation curves from a lot of different tests. And aside from these, they're usually also combined into an SN curve, where each point on this curve is one test tested to failure. These tests are actually accelerated, so you test at a higher strain level that is what is actually present in the real structure, so that you can extrapolate this curve out to using the design, real design. Yes. And the reason why the material actually degrades, the stiffness degrades during this fatigue test, is that we have damage initiating and progressing inside the material. Yeah, the damage is off-axis cracks, so then are initiating in the vacuum fiber bond. Sorry. And that we also see fiber fractures occurring in these load-carrying unidirectional fiber bundles, which are some of the damage features we see in this type of composite, but exactly in the order in which they occur and how they are connected is still not very well understood. And what found was that X-ray CT computing, X-ray computed tomography is a very useful method to looking into this damage progression and how it actually looks. So the idea of this method is that you have an X-ray source and an X-ray detector, and you place the sample in between, and then X-rays are emitted from the source and to the detector and penetrates through the specimen, and this gives contrasting the image depending on the material density. So then you rotate the sample, usually a full rotation, not always, and you store a projection image for each of these rotational steps. You can then use a reconstruction algorithm to recreate a 3D volume from these two images, which, for example, can look like this, which is similar to what I showed before. But there are some challenges using this method in relation to watching the damage. And one thing is that we want to look at broken fibers that are quite small features. The fiber diameter is usually in the range of 5 to 30 microns, so it's quite small. It's probably even smaller than that. And also interface cracks and matrix cracks, they might be even smaller, and we would like to see that, or I would like to see that. But the spatial resolution in the images, it decreases with increasing sample size. And scan time also increases. And spatial resolution also decreases with increasing field of view. And the image contrast is dependent on the material density. And what this means is that if we want to look at a large sample, which is the cross-section that actually matters, then we will get worse image resolution. And to obtain a high resolution, we can only look at a small volume, which is also quite relevant. And we might not actually see all the present damage features because this technique has a lower resolution than, for example, scanning electron microscopy or other techniques like that. So that's also important to consider. And if the crack faces in the material on contact, then there will be no difference in material density, so they will not be visible. It's also quite important to keep in mind. So these are some of the challenges that I've been working with in my project, and also how to overcome. And this. So now I'll get into my own PhD results here. And first, I'll just list how I'll go through them. So first, I will go into an initial study discovering where the damage initiates and how it looks, so how it's the shape of the damage region. And then I will go into monitoring the damage actually progress by ex situ X-ray CT fatigue testing method established. And this will be followed by applying tension to the specimens during scanning to see the effect of the damage. And also combining this ex situ approach with another experimental approach called transilluminated white light imaging, or camera and light. And I'll end up with presenting a 3D damage progression scheme established based on these observations. So starting with this first one, in this study, fatigue tests were performed on several specimens, and these specimens were then interrupted at a different number of load cycles, each individual specimen. And then cutouts were made from these specimens to obtain higher image resolution. And this was then examined by X-ray CT. And then from this, a lot of different damage regions were examined. I examined a lot of different ones. And what you can see an example here is these are the unidirectional fibers on this here. And these are the backing fiber bundles going out of the plane. Where you can see some examples of some broken fibers here related to a matrix crack, and there's also some broken fibers on the other side. And this is actually a 3D image. You have to remember that whenever I show some 2D images. But this is an example of how it looks. Then I did some damage segmentation in 3D on these images, and I will just show an example of that. So this is one of the considered volumes, and here we have the unidirectional fiber bundles, and the backing fiber bundles are in between here and down here. Now, if we make this invisible, or we make it transparent, it's called, and then mark the backing fiber bundles. Then it looks like this. The green is now the backing. Then mark the unidirectional fiber fractures. Then they appear like this. So this is the unidirectional fiber fractures I marked here. And what you can really see is that the damage is a 3D mechanism occurring in these bundles. And it's more clear maybe if you look from the top that it's really local around this region, which means that if you look in 2 dimensions, you might actually, depending where you cut, it might look different, which is quite interesting. So looking at all these volumes, there are different ones as well. My main conclusion here was that the regions where these backing fiber bundles were intersecting with each other, so a crossover region of the backing fiber bundles, and where they were also touching, you can say, the below unidirectional fiber bundle, that would be the most critical region for damage to occur. And this was where I saw the damage using these experiments. For example, it also means that a region like this one, which is on top of the matrix, would not be critical. So, yeah, fiber fracture damage is really a 3D mechanism, and seen mainly at these crossover regions of the backing with the unidirectional bundles. That was what was concluded here. So now for actually monitoring the damage progression by this ex situ technique. So this shows the overall idea behind this experimental approach. So fatigue tests were carried out in a regular fatigue testing machine, so outside the scanner, not inside. Then at some point the test was interrupted, stopped. The stiffness degradation was measured during the test. Then the specimen was taken out and put into the X-ray CT scanner, and a damaged region was scanned. Maybe some visualization was done, and then this loop was continued as many times as one finds feasible and until failure of the specimen. So, but how to locate damage? Now I mentioned earlier that we look at a very small region, and as you can see here, this is an example of a volume you might consider, and this is 2.5 millimeter in diameter here, and this is the specimen, and I tried to mark the approximate size of this in the specimen, and I told you also that the damage regions the damage is not homogeneously distributed in the specimen. So if you just choose a random region, then you might not actually see any damage there. So the way we did this in the beginning was to use a thermal camera to see a hotspot, and then interrupt the test and locate the damage that had already initiated by scouting zoom scan principle. So this shows the results from this study, where you can see the stiffness degradation curve is here. This is the measured stiffness degradation, and there are 4 interruption points A, B, C, D here. And this image shows an example of a 2D slice from the 3D data set of the point A, where we have the backing fiber bundles here that are going out of the plane again, and the unidirectional fiber bundles on each side here. And we have fiber fractures here, and also here. You can see these black lines that we have the fiber fractures. And then this is around 50,000 cycles, so if we cycle this 10,000 cycles more in this case, then there is damage has actually been seen to progress further into the bundles. There is an increased opening also observed with this damage. And even further cycling, more increased opening, further growth, and also new damage region occurring in the specimen, visible, at least become visible in the specimen. And here, very close to final failure, there is a lot of damage, and it looks like it's connecting actually to one another, this damage. And the specimen failed very shortly after this last image. So this gives a lot of information on how the damage progresses. But this is a 2D view. It would give more information if you could actually watch how it looks in 3D. So what I tried to do was to do some automatic segmentation of these fiber fractures. And what I did was to, initially align the initial state volume with the later state volume with each other, because when you take the specimen in and out of the scanner, although you might have a equipment that do that, it will still have some variation. So that was done in MATLAB. You can see now this is aligned, so it's moved a little bit to fit with the other volume, and then subtracting them from each other, which gave, you can say, that a volume which had all the differences between the two volumes, so the change in damage, you can say, which gave all the openings of the cracks and all the, well, additional damage that would have occurred. So now if you look at this, you can see that the broken unidirectional fibers are a lot more clear than they were before. I didn't show before, but they are, and that means that it's possible to use simple thresholding methods to actually get a quite good image of these damage, which I've shown here. The green part is now this subtracted volume, so the damage, and the unidirectional fiber fractures. And we have the unidirectional bonds are going up here, and these slice planes are on each side of the backing fiber bond layer. So on this side there is a 45-degree backing, and on the other side there is also a minus 45 and a 90-degree. And you can really see that the damage inside here is much different. Well, on each side it varies very much depending on how the backing locally looks on this side of the on the side that is touching the UD bond, which is quite interesting. So it's a very complex 3D mechanism, and it's also clear from this, which is highly related to the local bond structure. So, as you might also have thought from the XT2 study, the images, or the resolution in the images were, well, they were grainier, you can say. There was some noise in the image, which means that in some location you might not be sure if it's damaged or not. And to overcome this and make the damage more visible, we did these tension clamp experiments to actually apply tension to the specimen. And I'll talk about that now. So I will not go into so much detail about this. There's more in my thesis. But I've just shown an example here of the clamp on the specimen. It's like this. So the idea is that you load the specimen up without the clamp in the tension test machine. And then you apply the clamp to the specimen while the specimen is loaded, and screw and tie everything. And then when you release the tension on the specimen from the machine, then the gauge section is still loaded in tension. So that's the basic idea of this kind of solution. Then you can take it out and place it in the CT scanner and scan this region here. So this shows an unloaded region, a damaged region, with fiber fractures and a lot of damage. And now if we apply load using this solution, then you can see that if we go back and forth here, that the damage opens. And it's more clear if we zoom in a bit, so I made 4 different views here. And now in the unloaded state and the loaded state, you can see that there are some, it's maybe difficult to see, but there are some off-axis cracks in these backing fiber bonds that become a little bit more visible. And if you compare these two images, you can also see that there are some fiber fractures that were not so visible up here, but they're actually quite visible here with load applied. And furthermore, you can also, in some locations, the difference in the opening locally was actually twice of the fiber fractures. They opened almost double up by applying this strain, which is actually only around 0.17%, which is not very much. So this is also very interesting that it opens so much. And then in other locations, then there was almost no change in the opening. And then you can see here that almost nothing is visible up here, whereas you can see that some fractures actually are present. So it's clear that applying tension actually, applying tension made it clear that we don't see everything in these unloaded scans. So that's of course important to keep in mind. Yes, so I'll talk about combining this XT2 X-ray CT approach with the transilluminated white light imaging technique. So I included that this is the same loop as I showed before, but now here there's included a camera and an LED lamp on the other side. I'll get more into how that works. And what you can then get is that aside from the stiffness degradation, we also get the off-axis crack density as an output from the fatigue test, and then run this loop, as you can say. So, and then the idea is that we have this typical stiffness degradation curve for fatigue, composites loaded in fatigue, and then using this transilluminated white light imaging technique to actually monitor the off-axis cracks, in the backing, which generally occur relatively early in the fatigue life, and then using this ex situ fatigue, ex situ technique, and also tissue clamp experiments to study the unidirectional fiber fractures. So we say splitting it up into two parts. And what's also important to mention, in this specific study, the material was a little bit special. So instead of, but when we wanted to study the effect of one layer of backing in between two layers of unidirectional bundles, which is actually also the case in the blades, since you have so many layers of this fabric that it will be UD backing repeatedly, which means it makes sense to look at this isolated. And this was done by using two layers of fabric and then removing the backing from one side in the gauge section of the specimen. So, yeah, and that's really the case. So it looks like that. And now this shows this transilluminated white light imaging technique, or high resolution camera and light. And what you do then is that the images are captured during the fatigue test while it's actually fatigue testing at the max load at some chosen points during the test. So you obtain these images, and in these images you can see the off-axis cracks in the backing, which I'll get back to. Fatigue tests using this setup were carried out at different strain levels to test the effect of this accelerating the test if it actually affects the damage mechanisms. And yeah, the strain was measured in the same region as monitored by the camera to be able to compare. And this shows an example of this camera image in the unloaded state without any damage. So this is the full width of the specimen. Actually, the specimen is this one now, and it's the full width. And what we see here is actually the stitching thread here, these brown ones are the stitching thread, and the this checkboard, I don't know what it's called, is the field fire on the back side of the specimen. So the bundles themselves with glass fibers are invisible because they're in glass. Now we just one cycle, the initial tension test of this 0.6% strain, we get a lot of off-axis cracks actually already initiating after just one cycle. So we have, you can see some of the cracks are initiating from the edges, but others are isolated within the specimen, which is also interesting, and it could be related to the local bundle structure as well that they initiate like this. So cycling a little bit further, 1,000 cycles, we have a lot of cracks initiating already, and this is very early in the fatigue life. Maybe the sample is will last 3 million cycles or something. And then 100,000 cycles, it looks like this, and at this point it started to saturate actually somehow. And just to, yeah, so all these off-axis cracks generally initiate quite relatively early. So now looking at this, the crack density measured from these images using an automatic image analysis method, we can see that at different strain levels, the crack density develops differently. And especially also here that we have quite some scatter in where the cracks have initiated after already one cycle. So you can sense out the image of this. And that could also be related to the bundle structure, although not here. But now if you subtract this initial crack density from all the curves, then they look like this. So they collapse quite well on top of each other actually, which is also, I think, quite interesting. But what is also clear is that the off-axis crack growth is delayed at lower strains. That would be expected, I suppose. But you can also see, it's maybe difficult to see, but notice this is a semi-logarithmic plot. So these curves do actually start to curve. If it had been a non-regular plot, they start to saturate all of these curves. And you can see that it's not at the same level, which means that there is some difference in the off-axis crack growth behavior at the different strain levels, which could mean that there would also be a difference with the overall damage mechanisms, since they're highly related to the fiber fractures. So you can say one idea to how to actually use this to study the damage, or use this to consider the damage at the realistic strain levels is to use this sort of SN curve-like approach. So you can, at a given strain level, it will take this many cycles to reach a crack density of 1, for example, or of 2 or 3. And then use that as a sort of indication of the overall damage state. This is an idea for, we can say, future thoughts. So now also in the same, using the same material and considering the same, one of the specimens also considered by this transmediate twilight imaging is this XC2 X-ray CT test. And in the way from the one I showed before, it was different that say the last one, it didn't consider the initial damage state because the damage was found when it already initiated. But here the damage region was actually chosen based on the bundle structure by me, so that I could actually follow the damage from 0 cycles. And this shows an example here of a 2D slice view again of the unloaded and untested specimen. And this shows the corresponding image on the camera, so of this region. So it's actually looking from this side on the back. So 0 cycles, it's not really clear to see anything. 100,000 cycles, we start being able to see something, but it's not very visible. But you can see there are a lot of off-axis cracks that actually should be present, but we don't see any in this image at this resolution. And if we go a little bit further, it looks like there's some fiber fractures, but it's not very clear. And even further, they become more clear, and also a few more appear. After 500,000 cycles, well, I'm quite sure now this is fiber fractures, and also there may be some up here. So you see, it's clear that damage initiate and progress in this region, but it's not very visible in this case. Although we know there are a lot of off-axis crack damage actually present. So you can say, to look into this, how much are we missing? Also did some tension family experiments here. First in the initial part of the fatigue life. And then you can see here is an example of a region where there's only one backing layer. So that's where previously I didn't see any damage actually when studying this. But now, if we apply load here, there's actually quite a lot of fiber fractures that occur or appear. That it looks like there was not really any damage before, but now there is a lot of damage, and this is quite early in the fatigue life. And that must mean, I guess, that a lot of unidirectional fiber fractures actually appear much earlier than initially expected, at least also in the initial part of the fatigue life. And now looking a little bit later, just showing an example from that as well after 1 million cycles. Then in a different region here, you can see that that here there is a backing fiber bundle that is only touching the unidirectional bundle on one side. And if you apply tension, then you can see that there is actually even damage here in this region. And there's also the off-axis cracks here become a little bit visible, and also extends out into the matrix a bit. But what is also seen is that even when applying tension, fiber fractures were not seen in regions where the backing did not touch, you can say, the bundles, which is also important, I think. So, yes. So these damage mechanisms are highly related to the backing fiber bundles here. So to summarize the damage mechanisms I've mentioned throughout these presentations in relation to the off-axis cracks, well, it was found that they initiate and reach an apparent saturation state quite early in the fatigue life. And some initiate from the edges, and others they initiate in the center of the specimen, not center, but away from the edges. It's clear that they are related to the fiber fractures, that they are always appearing in the same region, you can say, connected regions. And the unidirectional fiber fractures, they appear as these 3D phenomena, and they appear as local features. And the damage, I didn't talk so much about this, but from watching all these results, then the damage is probably initiating and growing at different speeds, depending probably on the fiber bundle structure and so on, or similar. Yes, and the damage regions at the crossover regions were generally seen to be larger than at regions where it's just one vacuum fiber bond. So then, combining this into this 3D damage progression scheme that I tried to explain how I think the damage progresses is, I'm just going to try to explain here. So this is a unidirectional fiber bundle on each side of a crossover region of the vacuum, and also one single vacuum fiber bundle here, and they are touching each other here. So then, if we cycle a little bit, still within this initial stiffness degradation of this curve here, we have some off-axis cracks that initiate, and there are probably some associated fiber fractures that initiate, where it might be difficult to say they might initiate just after, or was difficult to say. And then after a little bit more cycling, we have off-axis cracks are growing and more are appearing, and probably also some more associated fiber fractures are occurring. Then further cycling, we will have some sort of getting close to saturation of the off-axis cracks, and the fiber fractures will start progressing into the unidirectional bundle in the different regions. This region is probably going to be larger than this region down here. With further cycling, getting closer to the end here, the damage region has progressed quite far into the unidirectional bundle, and with further cycle, progresses even further and connects to the other damage regions, and this then, you can say, leads to final failure. So, the final failure could be, for example, with the intralaminar splitting in the unidirectional bundle. This is what could be the case. So this is, yes, that was what my work, and I'll just do some conclusions. That I established these experimental methods that made it possible to monitor the stiffness, not to monitor the damage progression in 3D of these composite materials. And that can also be applied to other cases, of course. And it really gave some new understanding of how the damage initiates and progresses in these composites, which can also both be used to it can be used to improve the materials and so on. But it was found that the damage mechanisms were depending on the fatigue load level, which is, I think, important to also consider in the future, because it might actually be that we're testing something which is not the same as actually occurring in the real structure. Yes, and all this knowledge can be also used to improve the material. So finally, also this work shows the importance of and also sets the stage for X-ray CT-based finite element modeling, where you can include the real fiber bundle structure and the real fiber structure in your models. And I'll just briefly show some ongoing work and some that has been done in parallel in my project by using, you can say, the results from X-ray CT to actually extract the fiber centers using an algorithm by Monica from D2 Compute, Monica Amazon, and then import this into Abacus for further analysis as an example. And also, similarly on the bundle scale, which is ongoing work now, to segment out the bundle structure and then import into Abacus for further analysis. So this is, you can say, the future work path, one of them that I just wanted to mention. So that was what I had to say, and I would like to thank all the people who funded my project, and also my supervisors and everyone in COM, and all the research technicians. I could not have done this work without them. And I also want to thank you all for listening. So, thank you.